Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Klingberg, your host. Today's video, we're going to answer some questions that one of my viewers sent in. We're waiting for better winds here and do the next round of testing. I'm sitting here next to the pilot's cage and the center section's up here, and you can see I got it all repaired from the last, as one of my patrons put it, suboptimal arrival. Some people prefer to just call it a crash landing, but I like the other phrase. So I had a viewer here, his name is, I'm probably going to murder his name, Sunil Sundar, wrote in with really good questions. Now, before we move on to the questions and answers, let me tell you about a special offer I have just for you, especially if you're one of the many people that's been asking for a set of plans. Now is your chance. I know I've been saying no for a long time, a couple of years now. No, not going to be plans, not selling plans, not doing plans. Now that I've flown the aircraft once, I have kind of an inkling that it might be okay. I might be able to work it into a good design, nice flyable glider. I'm working on plans. I've been building plans in SolidWorks, 3D models, and at the end of this video, I'm going to tell you about how you can acquire a set for yourself. Use them however you like. And I hope you stick with the video and pick up the information at the end and finally satisfy that desire to have a set of plans. But here's the best part. They're free. You can get a set of plans for free. All you have to do is come along with me on the rest of the journey, and by the time we're done and we have a good flyable aircraft, you'll have a free set of plans. And what's better than free? You can't beat free. Stick around, check out the deal at the end, and now back to the questions and answers. So he wrote in and said, I have been keenly waiting for an update after your first real flight and rather bumpy landing. That's true. I have a few questions which I hope you won't mind answering. If they're good questions, I always love to answer them. So his first question is, and he was looking, this is reference to a video on the structural load testing we did on the wing. I'll put a link to that video in case you haven't viewed it. It'll be down in the description. It says, his question is, how do you test for torsional loads? And most of you probably hate the answer. I did and I didn't. The testing that we did, we load the sandbags at the quarter chord point, or 1/3 point. We put it right on the spar. And that's basically where the aerodynamic forces on the wing could all be resolved to. Now, because it's a swept wing, when you put the sandbags on the spar at the 1/3 chord point along the whole wing, you are putting the wing under torsion. If it were a straight wing, there would be no torsion. I have a straight wing like this, and I load it up, and it's just going to do bending. It's going to do bending up and down like this, no torsional loads. But if you have a swept wing and you load it up going aft, well, you're gonna bend it down and twist it. So you're putting in combined bending and torsional loads when you do that, because it's a swept wing. Now, that accurately represents a static situation in flight. You're flying along at one speed, one load, and that is the actual bending and twisting that's put on the wing that way. Now, what it doesn't cover is elevon deflections. You can deflect an elevon and put significant torsional loads on a wing. So how do we deal with that? Well, in the real engineering world, they have rather complicated, large test structures where they have a series of beams that span the chord of the wing, and they can both pull up on them and they can twist them like this. Those machines are complex and heavy and very expensive. So how do we simulate that or do something similar for an aircraft that we have no budget for or space for something like that? And the fact of the matter is in most cases, we don't. And before you start biting your fingernails off, it's like, wow, isn't that risky? Not so much, probably. In the design world where I operate and many home builders do, we're working on types of aircraft that it just happens to work out that by the time you design the wing to be strong enough to take the bending loads, it's also strong enough to take the torsional loads. And what happens is you get down to minimum material thicknesses for local buckling or just handling loads on the ground. And by the time you're down to that minimum material thickness, you can't go any lower because of handling loads or something else, or that's the thinnest material that you can purchase, and we're using carbon fiber. Well, you're already strong enough to carry the torsional loads. And that's usually the case. Build the wing strong enough to take bending, it'll take all the torsional loads. However, it's not always the case. Now, it is a rarity, and I've only seen one case where a wing actually fails in torsion. Usually if we're going to have a structural failure, the wing just folds up on the bending axis and sometimes goes aft a little bit to the weird loads that are on it in flight. If you're testing on the ground and you're putting straight bending loads on it, well, it's just going to snap in bending. However, I did run across a video, a pretty famous video, that I posted up for some of my engineering friends. I held it private for a while so we could discuss this particular in-flight failure. First of all, to take a close look at it and see, is it really a torsional failure? Did the D-tube actually twist and come off? Or is it a bending failure? And to me, it always looked like it was probably torsional, which would be a rarity. And I shared it with some friends and we agreed it's a torsional failure on the wing. And then we had discussions as to why. Could we understand why that wing failed in torsion so that I could avoid making a similar error with my design. And that video, that'll be the second link in the description. It'll take you over to that video. It's been very popular. I'll start off with the pilot wasn't hurt, used an emergency parachute, came down just fine. And it's the Aerooptrix foot-launched sailplane. Now that is a fantastic design. It is slick and clean and strong and really built for its business of being a ultralight foot-launched sailplane. However, it has a problem, same as my wing does, same as the Swift does. All of these ultralight foot-launched sailplanes will have the same problem. They are extremely slippery designs. We're getting into a high-performance region for these aircraft where you put the nose down, they'll go really fast. And because they're ultralight aircraft, the structure is so light that it is susceptible to gust loads or overloading with control forces. In other words, you could literally jerk back on the stick and snap the wings off. And normally you can't do that with most aircraft, but we're working into a corner of the design realm where that becomes a possibility. I'll tell you, my original wing, this wing, you put the nose down and all of a sudden you're moving, instead of moving 25 miles an hour, all of a sudden you're going 50 miles an hour. And it's really easy to push them up to 70, 80 miles an hour. You'd be going fast in a big hurry. They're extremely slippery, go quick, and they are susceptible to gust loads and drastic control input loads. And if we look at the Aerooptrix video, and the guy who was flying at the time said, yes, I overloaded it with elevator forces. I kept pulling back on the elevator. So what happened is he was doing aerobatics. He let the airspeed run past his maneuvering speed. The airspeed got up above the speed at which maximum controlled deflection would exceed the load capacity of the aircraft. That is a maneuvering limit. And then we have gust limits, and then we have just regular red line where you go too fast and the wings come off due to drag, which will go on to the next question. So if you go watch that video, you'll see a torsional failure, and it actually occurs, the torsional failure starts in the corner where the windows are in the wing. Now, I have an opinion about putting windows in a wing. I think it can be, especially if it's a high wing, it's a huge benefit for you to keep track of gliders that are above you in the thermal, and that can be a safety feature. It is also a design challenge. And if you're going to put windows in the wing, I think that the corners should be rounded off. I think some British designers on the Comet jet discovered that issue of rounding off the corners enough around the windows. And that one has square corners. I think it still has square corners, but they probably beefed up the structure. Plus, you shouldn't fly it up to a speed that exceeds the maneuvering velocity of the aircraft. That's a for sure way to fail the structure. But it did happen. So on my wing, I think I'll put up a still here somewhere. You'll notice a different coloration in the top of the wing. There's kind of a grayish white area, and then there's a really white area. The inboard portion of my wing, from the center line of the wing out to the end of the flap, that is a fully sheeted wing. That has composite skins top and bottom for the entire chord of the aircraft wing except for the flap. And that is to take those torsional loads. That if you were to really load this thing up heavy on the elevons, you're pulling a lot of up elevator and you're going to put some extra torsion on the wing or down. Elevon could cause the same problem. That there's a lot of beefy structure there. There's two spars. There's a main spar and an aft spar. And those skins, full skins top and bottom, create an extremely large torsional box that takes those loads. That box is way stronger than you would ever need to carry any normal flight torsional loads. So the fact of the matter is, never test for maximum torsional load. Is that risky? It could be. If I got into a situation where I oversped the aircraft, I'd either have to be very careful in pulling in some up elevator to slow it up and need lots of altitude to do that, or you know, we have an emergency system on all of these aircraft called the ballistic parachute, and it's a valid backup, although you're going to lose the entire aircraft, but you can always deploy the parachute. And so in an all-out emergency where if I were worried about overloading the structure or I didn't have enough altitude left to do a nice slow pull-up, I'd probably deploy the parachute. And then we get a chance to build a second aircraft, and the second one will be better than the first one. But I think that I've applied enough margin to my aircraft, kept the weight down, and provided enough margin. It's kind of like the Swift. All of the Swift versions were completely sheeted, and I don't know if they ever did any torsional load testing on that. I don't think so, but it's an extremely strong aircraft and has proved that over time through usage. So then the next question is, how do you test for drag forces? Well, that's just as hard to test for as torsional loads. And the answer is the same. Didn't. Usually the drag forces are so low compared to the bending loads or even the torsional loads that we don't even bother to go into that regime and test that. Usually that would be the red line limit of the aircraft. How fast can I go before the wing just folds aft? You know, that the drag loads just get so high that it folds aft. But because these wings are so clean, the drag forces are relatively low. So for the most part, we can say second order effect, ignore it and move on. And with the understanding that the wing's going to fail some other way first before it fails with just drag loads, and you'll be using the parachute anyway before it ever fails with drag loads. However, that said, my buddy Peter has run some Nastran program work on the wing. We've done a fairly detailed model in Nastran and checked for bending and torsional and drag loads, and we have a basic approximation of it. And the main thing that we found out in doing that work may not be the actual bending or torsional limits of the wing, but we found the ratio between the two, which is really critical. The ratio of the bending to the torsion and what would be its natural frequency of those two modes. And that's important when we get down to talking about flutter. Flutter can take apart an aircraft faster than just about anything else, and you want to make sure that the natural frequency of vibration in bending and torsion are not close to each other, that they're well separated, and that will help prevent flutter in flight. And with the Nastran modeling that we did, we found that there's a very significant spread between those two, so we're probably well protected against flutter. Not a guarantee, but the simulation says we're probably in the safe zone. If anything goes wrong with that simulation, the simulation is wrong. Emergency parachute, once again. So despite the fact that it seems like we're doing really high-end engineering behind this thing, a lot of the work that goes into it is based on best practices, which aren't necessarily backed by engineering, and just basic understanding of aircraft and aircraft design. What do I have to test for? What do I not test for? To make sure that the aircraft is relatively safe, that I can go out and fly it. And then when you fly it, you gently increase the flight envelope. When you first go out for the very first test, the flight envelope is a dot. Right in the middle, we don't know what the aircraft's capable of. Do some ground runs. Oh, okay, it'll take a G. It carries its own weight, takes a half a G. Oh, the first hop that I flew on. Well, we know that it carries 2 Gs plus a little bit. We rammed into the sand. The wing didn't break, so it takes some negative loads on it too. We didn't break the rear spar. No fittings broke, so there, we tested it. We tested it with a hard landing. That's one way of doing it. But little by little, we increase the flight envelope, and hopefully we do that in a safe manner, such that at worst, maybe you collapse the down tubes on the pilot's cage, but I don't get hurt, and the wing doesn't get broken, and we find out, oh, this is not strong enough, that's plenty strong, and you slowly increase that flight envelope. And as I get into the higher altitude test flights, we'll be exploring the speed range of the aircraft and its maneuverability, and we'll start looking at maybe some bending on it. We'll see some of the torsion that gets in the wing. My original wing, we did it that way. My original wing, we had a couple of cases where speed picked up considerably. We had to do a pull-up, and I could see the wing bending both up and torsion like this. I go, oh, that looks a little soft. You know, that was an awful lot of torsional motion for that amount of load that was put on the wing. Then we came back in and we put an extra layer of fiberglass on the D-tube for the first half of the D-tube span length. And the aircraft wasn't destroyed. There was no damage done. We landed. It's like, oh, but I saw something that probably is a little bit bigger than I'd like to see in terms of deflection, so we're going to go in and reinforce the structure, which is what we did. And that's quite often how these types of aircraft are designed, that a lot of the testing is done in small increments in flight, so that you have a chance to go back and make any corrections or beef it up as needed. Remember, the aircraft was designed for weight first before anything else, so I would not be surprised if there are some aspects of the design that are not strong enough for certain flight conditions or landing conditions and other situations, and we might experience more failures, and then we'll know what to go back and beef up and make it a little bit stronger. But that's the only way to hit the weight on the thing, was to design for weight and then very carefully increase that flight envelope and look for other potential failures. So that's what keeps the test flying a little bit exciting. We always know that we're taking a little bit of risk when we go out, and we try to have risk mitigation in place, you know, like emergency parachutes. So his next question was, Oracal 651 covering you use for the leading edge has a tensile strength of 19 megapascals compared to the burst strength of Oratex fabric, the polyester fabric, the UL 600. I know you are not using the UL 600, but rather the Oratex meant for model airplanes, which is around 0.4 megapascals. Now, this is a question from a viewer who's been he's been paying really close attention. Most people probably could not spit out numbers like this, nor have they even paid attention to the fact that I said, hey, I'm using model airplane version of the covering on my aircraft rather than the ultralight aircraft version. Why? To save weight, of course. And besides, the model version has the adhesive already on the fabric. Big plus. And it's cheaper. So that said, why? Why would I use this fabric on the wing instead of the vinyl covering, which is has a higher burst strength? Okay, so here's Oratex. Oratex is a polyester fabric, and it has color put on one side, and it has some heat-sensitive adhesive on the other side, and this is put on model airplanes, and it's just a thinner version of what goes on ultralight aircraft, and it is an actual fabric. Now, it has two main advantages that makes me want to use this for covering the open suit. So there is some ripstop effect to this, and in addition, it's heat shrinkable. You put this on the wing, you tack it down, you glue it down, and it's not tight yet, and then you come over it with a heat gun or an iron, and you stretch it tight. So with the Oracal 651, this is a sheet of vinyl. It is just a sheet of plastic. That's all that it is. And it's got sticky back on it here, always sticky, and a color on the other side. And this is meant for making vinyl lettering on signs. You take the backing off like this, and you can go watch my videos as I apply this to the wing. We put down some soapy water, just like they put a vinyl covering on a car, and you squeegee it out, and nice and shiny, it stays shiny. Only a little bit heavier than paint, not too bad. No toxic fumes, no messy cleanup, no spray guns to throw away. Really just super duper. And you can come later and use some adhesive softener remover and take it off if you want and apply new in case you have to do touch-up work. So pretty cool stuff, and really, because they make a gazillion yards of this stuff, it's really cheap. Now, the reason it has high burst strength is because you can stretch the bejesus out of this before it finally bursts. It is a stretchy material. But you know what? In the open structure of my wing, I don't want a stretchy material. I want something that doesn't stretch, like fabric. The fabric doesn't stretch, and this does. The fabric might not have numbers that are as high as the Oracal in terms of burst strength, but it doesn't stretch. And you want non-stretchy stuff for covering your open areas. The stretchy characteristics of the Oracal is super when you have to go around compound curves like my wingtips. And you can add a little bit of heat to this, and because it's vinyl, it doesn't burn too easy, but it does warm up and become very plasticized or plastic-like, and you can just pull it and stretch it and go around the most amazing compound curves with it. It's really cool. Its other drawback is not heat shrinkable. If I put this over an open structure and go to heat shrink it, well, it's almost like vac forming. It just sags and goes down in between the ribs. You can't heat shrink it, and that's because it doesn't have any pre-stretch in it, and it doesn't have any what they call memory to go back to the shape that it was before. So totally not applicable to putting on open structures. But I think in these little demos here, you'll see the methodology that I use for selecting a lot of my materials. It's one thing to go look at numbers and go, this one's bigger than that one, so why wouldn't you choose that? Or that's better than that other number, and isn't there some advantage in that? And I do some of that. I look at numbers in general, but you can't choose based on numbers only. You have to do what I just did here. You got to get the materials, get some samples in your hand, and play with them. Just literally play. And sometimes I'll sit while I'm doing drawings or something like that, and I'll just fiddle around with the material. Some of the pultruded carbon fiber I worked with, I did a lot of that. And I'll get several different materials, and I'll just mess around with them and use them in ways that they were never meant to be used, or just feel them in my hands. Go, what's it feel like? What's it behave like? What's its behaviors that are not listed in that product data sheet? What is not in the engineering data that I can feel with my hands and play with and see how bendy it might be, and use my knowledge that I've gained over 50 some odd years of designing and flying aircraft and say, oh, that's what I really want to use. Or there's a nifty property in this material that I could use to my advantage. And that is stuff that you can learn about a material only via playing with it, that they'll never tell you in the data sheets. So if you're designing an aircraft and you're wondering about the numbers, well, just get some of the material and start playing with it. Lay down some samples, diddle with it, and you never can tell. Keep an open mind. You never can tell what you might run across, some strange phenomena of that particular material, and you go, oh, that'd be pretty cool if I applied it in this way to the aircraft. And you have to have some experience with aircraft and design work in order to take the best advantage of that. But there's a lot of information that is buried in the material itself that is not listed in the product data sheets that can come in very handy when it comes to design. And it may not help you on that particular design. This might be information that you collect about that piece of material or epoxy. Oh, this resin has this type of viscosity. I see what it feels like on my fingers. Oh, I wouldn't want to use it for that type of layout. I'd want to use it for this other work. That is stuff that you gain as you go along. Might not use it on a particular design, but you use it later on some other, you're doing a boat or something. So there, that's how I choose materials sometimes. It's not very scientific, but it's very effective. So there we are. And I think we finished up his questions. I hope I covered them thoroughly. And I hope you stick with a little bit more of this video because, as you know from what I told you at the beginning, I got a great offer coming for you at the end of this video. I think you're going to be very interested in plans for the aircraft and how you can acquire a set. So he finishes up here by saying, on behalf of the world, I'd like to thank you for sharing your knowledge and innovative problem-solving techniques on YouTube. Well, that's a mighty big thank you. He's thanking me on behalf of the entire world. I'm sure there's really a very small, tiny subset of people in the world that are actually thankful, but thank you very much, Sunil, for doing that. Okay, so I brought you over here so you can get a close look at the new control stick. This is one of the big projects in the upgrade. The previous control stick had some binding in it. How I had these turnbuckles hooked in and some other stuff set up, there was binding in here, and the loads were pretty high. And this was previously an aluminum tube here. The torque tube was aluminum, and it was actually getting some flexing in it. So I've switched that out for 4130 steel. Thanks to my buddy Bob for doing the welding here on the side fitting for the differential gear. And I did new control horn style here, and you see you can go all the way like this, and the offsets leave room for the turnbuckle there. It's some nice paint and so forth. So we're looking a little fancier now. And I got some of the binding out of the roll function here. I put on a new control stick, a nice rubber one. Thank you, Schwinn, for a nice little rubber control handle there. It's actually a bicycle grip turned around backwards. This new stick here is actually 3/4 inch diameter carbon fiber tubing with aluminum tubing insert. Don't worry, there's anti-galvanic coating in between the two. And it is offset to the side here so that it's a little easier grip for me. It brings it a little closer to the center line of the cockpit, a little easier grip. And this is carbon fiber plates on either side and then wrapped with unidirectional carbon fiber around it. So a nice strong control stick there. Push rod here was switched to aluminum for carbon fiber, a little bit lighter. So the whole thing is nice and smooth and easy now. It's got some extra pads here so that when we fold it up, it doesn't damage the tubing. So just a very sizable upgrade all the way around. I also put in a wavy washer in here. You can't see it, but this stop fitting here pushes up against that wavy washer. It's a spring-loaded washer, and that puts a load on this gear in this way, in this direction, making sure that the elevator gear is always tight to the other two gears, so that took slop out of the system. There used to be quite a bit of slop in the system, and it's almost entirely gone now. And I did some other work on the elevons. I changed out the hinge pins on the elevons and reduced loads out there. So I've taken about 75 or 80% of the controlled drag loads out of the system. And that's a big help. So the loads on control stick when you're static should be much lighter than they have been in the past. So those are some significant upgrades. And in the process, I've created SolidWorks 3D models. I'll put up a picture here that I'm still working a little bit on the control stick assembly model. And it's been very helpful in terms of looking at interference and other fittings and just doing the overall design. And these control horns were actually made directly off of those 3D drawings, 3D models. So, wow, accuracy. Something that we didn't have in the original get-go. And in fact, that's what I'm actually doing now. Most of the evenings while I'm waiting for good test conditions, I'm sitting at my computer in SolidWorks and I'm drawing up all of the components to the aircraft that I know work. And that's what I'm going to make available to you, my viewers, via a special program that I have over on Patreon. I'm going to put in the link for Patreon. Many people have said that they'd like to buy a set of plans for this aircraft, and I told them, I don't think there's ever going to be plans. There might not ever be plans. I don't know. I don't know if the aircraft's going to fly right. Why should I do a bunch of plans and not going to? No, I don't have any plans for sale. But there's been enough demand for that, and I think that I'm on the cusp of having an aircraft that flies decently, so I'm willing to go in and put in that work and make a special offer available to you. What I'm going to do here, what I am currently doing, is for anybody who's a patron at the appropriate level, and when you go to Patreon, you'll see the level for that, and you're going to help support the test flying of the aircraft. There's still a lot of testing to go. We've made just a short little trips down to the beach to test it out, but there's a lot more to come. Testing's very expensive. There's travel, there's gas, there's hotel, there's all kinds of expenses, and they're quite high. And any support that I can get from you to help support that testing, I will show my gratitude to you by giving you a free set of plans for the glider. And I do mean free. There will be no charge for the plans for the glider, but you will be making a monthly contribution to the test program, which is fantastic because we need to get that done. And as I go along, incrementally every month, I'm releasing a package out to my patrons. In fact, all of my patrons currently have the first package, which is all of the wing fittings. All of the fittings that attach the wing parts together. I've finished those models and I've sent them out to my patrons. And you'll get the full set. You won't just get an assembly that sits still and doesn't do anything. You'll actually get a functional SolidWorks model. And not just the assembly, but you'll get all of the components that are in that assembly. Every single component that's in there, from the smallest bushing to the bevel gears to everything. It'll all be in there, and the files will be there for you to use as you see fit. I can't sit here and say, yeah, you should start building one of these things based on those drawings that I'm sending out, because we don't know if the aircraft's really going to be any good yet or not. However, you might find models in there, a model of a bushing or a carbon fiber tube or something like that, that you might be able to use on one of your own designs or modify it and use it in something that you're working on. And if I get to the end of this thing, we get all the way down to a nice flying aircraft, and maybe a year from now, I've finished up all of the sets of models of the 3D drawings, you'll have a complete set. You'll have all of the details of the aircraft, from the smallest cotter key on up to ribs, spars, and the whole bit. And if you combine that with all of these videos that I've put up on YouTube, you could literally go build one of these for yourself. And not only will you get the 3D models, but you get the bill of materials too, because that's one of the cool things that comes out of SolidWorks. For every part that I put in there, you will get the part number if it's bought off the shelf, and you'll have a list of where you can go get that, whether it be Aircraft Spruce or some other fitting supplier, bolt supplier, or whatever. And that full bill of materials will be in there. Thousands of parts. You'll get a nice Excel spreadsheets that you can use to keep track of the bill of materials. And you want to know what it costs to build it, you can go then research each one of those parts and figure out what it costs to build one of these things. And if you figure that out, let me know. Don't tell my wife, please, but let me know what it cost me to actually build this thing, if you ever figure it out. So there we go. That's the offer. And if you want a full set of plans, I can't guarantee you a full set of plans, but I can guarantee you that as long as you stay a patron, and as long as I continue to make progress on the design and get it tested, I'll continue producing sets of 3D models until the aircraft is done. Hop on board now, support the testing, get a free set of plans. For a little aside here, one of the other changes that I'm going to be testing out on this coming Tuesday, we hope, if the winds stay the way they are, is Vortellons on the leading edge of the wing. Put up a picture here of Vortellons. Vortellons generate a vortex on the top of the wing, and I'll put a link into Wikipedia that explains about Vortellons. You can go read more about them. And I've created and built a set of 3 Vortellons for each wing, and I'm hoping to keep the flow a little better attached to the elevons when you're ground handling, so that you have a little bit more control authority. And you can see them in the picture here. The design of those Vortellons I stole from the Long-E's, the Rutan Long-E's aircraft, and I just sized them using TLAR, T-L-A-R. TLAR, that looks about right. In other words, I eyeballed it for making the size of those Vortellons, and then I put some plastic protective material on the wing, molded fiberglass right to the shape of the wing, and glued the Vortellons onto that, and then cleaned them up. And I can tape them on the wing, I can move them around a little bit and adjust and play with them and cut different sizes until I have something that gives me the positive effect that I'm looking for. Okay, so thanks for watching today. I hope to hear from some of you concerning the plans. I hope there's enough interest in that. And just hop on over to Patreon. It has all the instructions over there. Links in the description. And I hope I've been able to answer the questions correctly and sufficiently, and I hope I've brought you up to date as to what's going on with the design. And I thank you very much for sticking with me through all of these videos. It's kind of a journey we're all on together as we discover whether this is a viable aircraft or not. And however it turns out, it's an exciting journey along the way. I hope you're having some fun. I know I am, and I hope you continue to stick with me. I enjoy doing this, and in a couple days here we'll go out for some more ground testing, and we'll gain some more knowledge, and I'll come back and share that knowledge with you. And until then, I'll remind you, fly safe, and bye for now.